circular motion. Let me talk about constant speed circular motion. So a constant speed circular motion does the following. R cosine omega t, R sine omega t. So as you can see, this omega is a constant, so it has a constant angular velocity. You're going to see later why this is called the angular velocity, but right now, omega being fixed, that means it's rotating around the circle in a constant speed. And because r is also fixed, it's really going around the circle. Okay? Now, I'm using the same r for this and the function itself. But the reason I can do that is because if you find the norm of r, think about the norm of this vector. See, it's a vector valued thing, so definitely you can take the norm, or you can take the magnitude of this vector. How do you do that? Take the square root of each. And then that's r squared cosine squared omega t. That's also sine squared omega t with the cosine squared, r squared in front. So it's r squared sine squared t from here. So I can factor the r squared out. What's cosine squared plus sine squared if they have the same angle? 1. And since these agree, this squared plus that squared gives you 1, giving you r squared times 1, which is just r, assuming that r is positive. We're going to assume that r is positive. Because I want the r to be the radius of the circle. Okay? All right. So really, I'm using this r without the arrow on top as the magnitude of the vector r. And that's a standard practice. So whenever you have a vector v, then the magnitude of this vector is denoted as v without the arrow on top. That's a standard practice. In fact, if you in most physics books, if you open it up, you'll see that this is the way people write it. So, you know, in physics books, they actually write the bold-faced font for vectors, right? So if you have a bold-faced v and a regular face v, then you should understand it as the vector version's magnitude being written as the regular face, regular font. Okay. All right. So this is why I'm using r as the same thing as here, and you probably understood that this means that the distance from the origin for this vector is always r, regardless of the value of t, which means if you collect all the points that are distance r away from the origin, that's going to give you a circle, right? So that's why this is a circular motion. Now, to see that this is really constant speed, let's find the velocity. That's the derivative, right? Which is negative r omega sine omega t, comma, r omega cosine omega t. Okay, so that's the derivative. Is this a constant vector? Is the velocity constant? Yes or no? Is the velocity constant?
No.
No, because it's a function of t. It changes, right? So the velocity is not constant. Of course, we're thinking about circular motion. The direction is always changing, so it can't be constant velocity. But if we calculate the magnitude, if I take the norm of the vector, then it's square root of negative r omega sine omega t squared plus r omega cosine omega t squared. I can pull the r squared omega squared out, and what's left is sine squared omega t plus cosine squared omega t, which is, what's this plus this? 1. So you get r squared omega squared, square root of t, square root of that, which is r omega. Oh, okay, I'm even assuming omega to be positive, just for simplicity. Omega being positive means that you're going in the counterclockwise direction. Okay. It's not too important. All right, so you have r omega equals to the speed v. So using the convention, v is the magnitude of the velocity. Magnitude of the velocity is called the speed. So we just found that the speed is equal to r omega. Is this constant? Yes, this time it's constant. So in fact, we proved that this vector valued function describes a particle moving in circles with constant speed, r times omega. Okay? And here we also find out why omega is called the angular speed. That's because if you take the velocity and divide by the r, right, which is r is the radius, we get the well, actually, it comes from something else. You know, there's this formula, SOAR. You know, have you ever seen this formula, SOAR? It really means if you have radius r with central angle theta, then this arc length s is this. Okay. Now, if you say this is a circle so that r is a constant, then if you differentiate both sides, you get the following. Okay? So basically what you're saying is the rate of the change of the arc length, which is the speed, right? If you differentiate the position, you get the velocity, but if you differentiate the distance traveled, you get the speed. Right? Okay. So this is really v. And then if you think about what this is, that's the rate of change of the angle, right? That's the rate of change of the angle, right? That's how fast this theta changes as this thing is moving. So when theta is small, you're here, and then theta increases with time, right? So you're looking at how fast this angle changes as the particle travels around, right? And that, because that's the rate of change of the angle, that's really omega. And that agrees with this one, right? V is equal to r omega. So rather than saying that we find out that omega is the angular speed, we know that omega should be angular speed. Anything that satisfies this should be called the angular speed. And from this, we see that, oh, omega should be placed in here. Okay. So it just agrees with everything. Okay, so from this calculation, we agree that this coefficient of t that was inside should be called the angular speed, because we know that if there was such a thing as angular speed, it should satisfy v equal to omega r. So that's what we find so far. Okay. Now here's another interesting observation. if you do r dotted with omega, what do you get? How do you do the dot product? Component-wise multiplication, and then you add, right? So if I multiply these two, you get negative r times r is r squared, and you get omega, and you get cosine omega t and sine omega t. That's what I get from these two. If I multiply these two, it's positive r squared omega times sine omega t and cosine omega t. Aren't they the same, right? So you get 0. Okay. What does that mean? If the dot product is 0, we know that.
Same direction. Oh.
No, that's for cross product. If cross product is 0,
Perpendicular.
okay. So to summarize, if the cross product is 0, you know that the two vectors are in the same direction, or it could be 180 degrees, either 0 or 180 degrees. Okay. If the dot product is 0, we know that they are perpendicular. Okay, it's very important to know this. Okay. All right. So since the dot product is 0, we know that they're perpendicular, and it only makes sense because think about it. At any time t, this is your rt because rt is the position vector. Okay? It's a vector which starts at the origin and its terminal point is at the point where the particle is, right? So it's a vector that's originating from the origin from the end of the circle, right? But at this point, what's the direction of the velocity? It's tangential, right? Velocity is always tangential. So of course it's perpendicular, right? Or you could say, if you didn't know this fact, you can say that the tangent line of a circle is always perpendicular to its radius. That's something that you learned in high school, right? And here's a calculus proof of that fact. Okay? So you can think of it that way, right? Okay. What else can we do? Let's say we're doing physics and we found the velocity and we got these. We got this as an achievement. Right? What else can we do? Acceleration. Acceleration, right? How do you get the acceleration? You differentiate one more time. Right? So we differentiate one more time. Acceleration vector is v prime of t. And that's, if I differentiate this, that's negative r omega squared cosine omega t negative r omega squared sine omega t. That's the derivative. Differentiating cosine gives you negative sine. And because of the chain rule, omega t has to be pulled outside, and you have to differentiate omega t, which gives you omega. That's where this extra omega comes in. All right, and then what's the norm? See, at this point, it's, here's another way to think about it. We can just say that this is negative omega squared r cosine omega t, r sine omega t. Okay. What's this? Huh?
0.
No.
R.
R, that's r, right? That's the r vector. You're multiplying by negative of omega squared. So let's forget about the size and just focus on the direction. It's negative of r. What does that mean? The direction of the acceleration is opposite of what? The position vector. So in this circular motion, this is r. Where's the direction of acceleration? Okay. Using F equal to ma, what does that mean? The centripetal force is
Acceleration.
opposite of the radius, right? when you have a circular motion, the centripetal force is always pointed to the origin. That's what we learned. For constant speed motion. Okay? And that also tells us that since this is v, again, v dot a will be 0. V dot a is 0 because r and v is 0. Okay? We can actually calculate that. Okay? So that they're perpendicular, in other words. We know that acceleration is perpendicular to this constant speed motion. Okay, and then finally, what's the norm of A? Well, the norm of, so here's how you can do the norm without actually having to do all this again. We know that A is negative omega squared r, right? This is r, so this is really negative omega squared r. And negative only changes the direction, so negatives don't do anything in terms of the size, right? So we can just do this. And if you are multiplying a scalar to a vector, some positive scalar to a vector, that's same as first figuring out the size of the vector and multiplying that scalar to it. Right? So I should have mentioned this formula a long time ago, but here's the formula. If you have a constant times a vector v, and you wanted to know the size, it's really the same as taking the absolute value of c, because negatives don't matter, times the value of the length of v. So that's a handy formula for you to know. And therefore, you have this. We know that it's r. That length is r, so we know that it's r omega squared. So acceleration is r omega squared. We've seen this before, right? Now, if you haven't seen it before, look at it this way. Here, omega is v over r, right? So if I plug that into this formula, a is equal to r omega squared. Acceleration is r omega squared. If I replace omega by v over r, we get r times v over r squared, which is v squared over r, because this is r squared, and r cancels, and we get v squared over r. So acceleration is v squared over r. That's the formula that you learn in physics. They do provide you some proof, but it's not really convincing that much. Sometimes I read these physical arguments and I don't really get convinced that much. But if I see the actual math done, it's very convincing. Okay? So that's what we just figured out. We just figured out that the centripetal acceleration is same as v squared over r. Speed squared divided by the radius gives you centripetal acceleration. So it's a pretty neat result, just using calculus.